Hi math students, this video will focus on domain and range. I wanted to start with probably the most basic type of domain and range question that you'll see, and that's if you're given a plot and you're asked to find the domain and range provided. In this case, we have, looking at problem number 1 directly out of our textbook, we have part of what appears to be a quadratic function. Now remember, if I'm asked to answer or to determine the domain, I need to think about what the possible input values are. What are the values that could go into the function, or what are the set of input values or x values that you see? And one way to do this is to take a vertical line, if you can imagine, and then shift that vertical line back and forth and ask yourself where you're intersecting the function. In this case, my lower bound is 1. My upper bound is 7. And so one way in interval notation here to say to state the domain of this function is lower bound from 1 to 7, and these brackets, remember, mean inclusive. Another way to write this would be x is greater than or equal to 1, less than or equal to 7. The range for this curve. Take a horizontal line. Ask yourself, where are you intersecting the function? And again, if you're answering a question about range, you're saying what are the possible values that can come out of a function? What are the possible outputs, or what are the y values, or f of x values in this case? I've got my horizontal line. If I were to shift that thing up and down, where am I intersecting the graph? I'm intersecting it from here all the way up to here, and so we say that our range is 2 to 18 inclusive. Another way to say it would be y is greater than or equal to 2, because we can get 2 out. Right here we get a value of 2 out, less than or equal to 18. You might say real numbers greater than or equal to 2, less than or equal to 18. Again, different ways to state this, all inclusive, and in many calculus classes in the future you'll see interval notation. So right here. Okay, I'm going to pick up the pace a little bit. Number 2, what is the domain of this function? The lower bound is 2, the upper bound is 6. And so we would say domain 2 to 6 inclusive in both cases. The range, what's the minimum output that you see? The minimum y value is 1. The maximum y value appears to be 3. And so we're going to go from 1 to 3. Remember, your left value here is your lower bound, your right value is your upper bound. The comma, this is not an ordered pair. That comma just separates the lower bound from the right bound. So range 1 to 3. Number 3, I've got a semicircle. Let's look at our domain. Lower bound of our domain is an x value or an input of 0. Upper bound is an input of 4. We would say for the domain 0 to 4, again inclusive. Our range, what are the possible outputs? Well, I go from 0, and there are 2 times that we intersect, we have an output of 0, from 0 up to the maximum range, the maximum, I should say, output of 2. So from 0, lower bound, to 2, upper bound, again, still inclusive. So we've got brackets, not parentheses. You'll see some examples later using parentheses. Next, domain from 1 to 5. So my domain has a lower bound of 1 and an upper bound of 5, and my range, lower bound of 1, upper bound of 6. Okay. In the previous examples, you were given graphs. In this example, or this set of examples, you're not given graphs. However, let me say, I want to strongly encourage you to graph these functions on your graphing calculator. Then you will have a graph. But I'm going to talk about the algebra behind these as well. So as we've mentioned in class, you can only take the square root, in this case, of a value greater than or equal to 0. Okay, we can't take the square root of a negative. And so I might say initially 16 minus x squared has to be greater than or equal to 0. Well, you can think through this a little bit. You can plot that now as well if you wanted to. But let's talk about what would make 16 minus x squared greater than or equal to 0. I need values such that this whole thing is greater than or equal to 0. And the only way that that can be true is if x is greater than or equal to -4 or less than or equal to +4. I'd encourage you to pause and think about that for just a moment. But x is going to have to be greater than or equal to -4 and less than or equal to +4. Okay? Otherwise, we have something that's not greater than or equal to 0, and if we have something that's not greater than or equal to 0, we cannot take the square root of it. So I can only put values in that are true for this statement. So my domain, at least that's what my gut is telling me, we're going to plot it in a moment, my domain is -4 to 4. Now let's see what our gut tells us about the range. What could come out of this function? Well, we've talked about it in class, and hopefully you're getting more comfortable with the idea. If you're taking a square root, the only value that can come out in this instance is a number greater than or equal to 0. So we know that the range, the lower bound for the range, is going to be a value greater than or equal to 0. Now the question is, what's the upper bound? Well, it gets a little complicated, and it's definitely worth plotting this function, I'll state again. But think about it. If you start with 16 and you subtract something, the smallest value that you could subtract possible would be 0. And if you subtracted 0, the square root of 16 would give you 4. Not plus or minus 4, it would give you 4. If as x gets bigger, as this x value increases, and again, we know that this x value can only go between -4 and 4, but as this x value increases, 16 minus x squared will decrease. And as that 16 minus x squared decreases, if we take the square root of it, that value is going to decrease. And so that should tell us that the maximum possible output is actually going to be 4, and that 4 would occur if x is 0. Now, let's graph. So I'm going to take a moment. I'm going to plot it. I'm doing that off to the side. Y is equal to the square root of 16 minus x squared. And on my calculator, I'm going to hit zoom option 0 for zoom standard. I'm sorry, not zoom 0. Zoom 6. I apologize. And that gives me the following graph. Let me just sketch it. It gives me this. I see a semicircle with a maximum, if we look carefully, at 4 and a minimum of -4 for my domain and a maximum of 4 for my range. Now, your semicircle, when you're looking at the calculator, it almost looks like, and this does it to me, it almost looks like it gets cut off. It looks like it stops like right here and right here. It doesn't, okay? It's just a restriction of the calculator. Keep that in mind and think about the algebra that we talked about. So domain -4 to 4, inclusive, range 0 to 4. Let's look at another. That was a tough one. We'll take it back a step for the next couple of examples. So next example, I have g of x equals 5 minus x squared. Now we know that this is a quadratic, and it's a downward facing quadratic. We can plot it, and hopefully you know what this looks like already. If you don't, that's okay. But by the end of the course you will. It's a downward facing quadratic with a y-intercept of 5. So it looks like this. Now, what's the domain? What's the range? Well, let's talk about the graph, and then we'll relate it back to the algebra. My domain is all real numbers. Another way to write that, -infinity to +infinity. Notice this is the first time in interval notation that you've seen in these examples, that you've seen the parentheses. We don't include infinity. Infinity is an idea. It is not a value. Now, what's the algebra behind that? Well, think about it. You can put, the question about domain is, what can you put in? You can put anything in to square and then subtract that from 5, and you'll still get something out. So we can put anything in and get something out. For the range, take a look at the graph. We can see that the maximum output occurs at 5. And if you took this horizontal line and you shifted it down, up and down, you'll always intersect the graph when you're below 5, you'll never intersect the graph up here above 5. And so our range, we would say, one way to say it is all real numbers less than or equal to 5. And the interval notation for that is, let's see, negative infinity would be our lower bound, and 5 would be our upper bound. Notice the parenthesis, we use a parenthesis on any infinity. And in this case, we've got a bracket on our 5 because we can get 5 as an output. If I put 0 in, I get 5 out. Next, h of x is equal to negative 1 over x. H of x is equal to negative 1 over x. Maybe you know what this graph looks like already. If you do, that's great. It looks like this. Okay, let's talk about why. We cannot put 0 in. We cannot put 0 in. If you put 0 in, you end up with a 0 in your denominator, and we say that when you divide by 0, you're undefined. So that tells us something about our domain. Our domain is all real numbers not equal to 0. Okay, you cannot put 0 in. The way to write that in interval notation gets a little tricky. Negative infinity to 0, union 0 to infinity. Notice I'm using parentheses here and here because we don't want to include 0. But what we're saying is if I took a vertical line and I shifted that thing back and forth, okay, the only time that I don't have a point is when the x value is 0. And now that I've said that, that's a nice lead into the range. You have the only output that you don't get. The only output that you don't get is 0. You've got your vertical asymptote, the x-axis. You've got your horizontal asymptote, the y-axis. Your range is also all reals not equal to 0 for this function. I'll do a couple more, and we'll stop. So j of x is equal to 3 over x squared. Again, I would encourage you to graph. We'll go ahead and graph that. So 3 divided by x squared. If I plot that curve, it looks something like this. Positive 3 divided by x squared. Notice it's not 3 times x squared. If it were 3 times x squared, it would have looked like this. That's not what we have. We have 3 divided by x squared. Now, domain. Question is, what can go in? Or in this case, the easier question to answer is, what cannot go in? Well, I can't put 0 in because 0 squared causes a problem. So my domain is, once again, all real numbers not equal to 0. That's the only restriction on this curve. Okay? I'm going to put a question mark here, and I'm going to say, do you remember how to write that in interval notation? I would like you to be able to write that in interval notation as well. Range. Think about your range here. What possible values can come out of this function? Well, I have a horizontal asymptote, and then if I were to, and the graph, by the way, will never intersect that x-axis. I cannot get 0 out, but I can get anything else out. Anything greater than 0 I can get out. Draw your horizontal lines. Where are you intersecting the graph? Okay, I'm intersecting it everywhere greater than 0, and so my range is all real numbers greater than 0, and an alternate way to write that, 0 is my lower bound, infinity is my upper bound. Notice I'm going to use a bracket. I'm sorry, that should be a parenthesis. Notice I'm going to use a parenthesis because I'm not including 0. All right, I'm going to jump down to L of x. And if we have time, I need to stop this video in about 2 minutes. I may not have time to do k of x. Let's talk about L of x. So 1 over x squared plus 3. Now, again, I would encourage you to plot that first. Now, when you type this into the calculator, be sure to wrap that x squared plus 3 in a pair of parentheses. Otherwise, most graphing calculators will misinterpret what you're asking it to do. Now, in my case, I'm looking at my graph right now. I get something like this. Not real helpful. So I'm going to zoom in. You can hit the zoom key on the graphing calculator, and I'll choose option 2, and I'll zoom in a little bit. Okay? And now when I zoom in some, I get a graph that looks a little more like this. Okay? Not perfect. We could zoom in more, but it's enough for us to determine our domain and our range. And so let's think about it for just a second. Domain. What can go in for x without breaking any rules? Well, because I'm adding this plus 3 here, there's no way for my denominator to equal 0. It will never equal 0, which tells me that I can put anything in. My domain is all real numbers. If you look at the graph, switch colors here. If you look at the graph and think about this set of ordered pairs and it's going forever in both directions, you can put anything in, including an input of 0. Okay? If I put 0 in, 0 squared plus 3 is 3, and we get 1/3 out, which 1/3 is actually your maximum output. That's your maximum y value or your y-intercept. Let's think range now. What could come out? So again, the function, let me rewrite it, 1 over x squared plus 3. What could possibly come out? Well, x squared plus 3 will always be positive. No matter what you put in, it's going to be positive, which means that I have a positive divided by a positive, and a positive divided by a positive results in a positive. So what can come out? Only a positive. Now the maximum value again occurs at 1/3. When I put 0 in for x, I get 1/3 out. So our range is actually 0 for our lower bound, 1/3 for our upper bound, and now let's think about parentheses and brackets. We'll include 1/3 because I can get 1/3 exactly. I can get that exact y value right here. Okay. We will not include 0 because we have a horizontal asymptote. As x gets bigger, write it one more time, 1 over x squared plus 3. As x gets bigger, my denominator gets bigger. And as my denominator gets bigger, 1 divided by a bigger and bigger number goes to 0. That's why as the graph approaches, as the x values head towards infinity, the y values go towards 0. The same thing happens as I move x values towards negative infinity, and I'll let you think about that. All right, that's all I've got for you. I'll post another video on domain and range soon.